Awesome. Okay. Well, good morning, everybody. Thank you for coming. I'm Yuan Kang, and I'll be talking about our paper on automatically detecting error handling bugs. Incorrect error handling is a major source of security flaws. In fact, the Open Web Application Security Project ranked it as one of its top 10. And as you can see here, it's been behind a lot of bugs that have been serious enough to warrant their own CVEs. These bugs are especially problematic in C. Why? Because unlike Java, you don't have built-in exception handling mechanisms. In C, you bring your own exception handling mechanisms. For example, here we have func1 returns 0 for error, while func2 returns a null pointer for error. Keeping up with all these conventions is tedious and hard to get right, especially when you're busy programming. How bad can it be? This is how bad it can be. This is one of the many CVEs I just listed. It happens in GnuTLS, one of the popular TLS libraries. Here, the program calls checkIfCA. That function checks if a certificate belongs to a certificate authority. Figuring out this property correctly is very important because a certificate authority can issue arbitrary certificates. That means if we have a malicious authority, that authority can pretend to be anybody by just issuing a certificate for that party. As we see, the program checks if checkIfCA returns 0. That would mean that the certificate says that it does not belong to a certificate authority. And that sounds pretty reasonable, but what happens if the certificate does not say anything because it's malformed? Let's actually see what checkIfCA does. We see that if an error happens, result is less than 0. And when it's less than 0, the function skips right to the end and returns that value. Unfortunately, the caller does not check for the negative value. Result is set to 1, even though the certificate is malformed and does not actually belong to a certificate authority. That means an attacker can just spoof anybody by just issuing a malformed certificate. Well, if this is so bad, then why don't existing tools check these? There are a couple of problems when dealing with error handling bugs. First, they rarely show up during regular execution. So traditional testing and static and dynamic analysis will be hard because most of the errors don't ever show up. Second, even if you do find the bugs, most of the time the crashes aren't going to be something obvious like a crash, even though they do produce incorrect results. That means we need some kind of error oracle that tests if the error is being handled correctly. And yes, you can sit down manually for every function, say, okay, this is how it should be handled, and if it's not handled like that, then we have a bug. But that's very tedious and not very scalable. We need something that's more general to any kinds of programs that we want to check. Related to that problem is the issue of bug localization. We don't only want to know that there is a bug. If we ever hope to find it, we need to know what caused it. The problem is, especially for these kinds of silent bugs, is if they do appear, they appear way after the cause actually happened. And that makes localization very hard. This is where EPEx comes in. It is an automatic tool for detecting error handling mechanisms. It stands for error path exploration because we need to explore different paths. Problem is, there are a lot of paths. How do we cut down to what's necessary? We perform under-constrained symbolic execution. In particular, we only look at the caller of the test function that could fail. And yes, because we don't do full symbolic execution, that's going to introduce a lot of paths that might not actually be feasible. But it's a good trade-off because, as we will see, most of the error handling only happens during the caller, or if not, then it's probably too late. And amongst those shorter paths, we only look at those that are error paths. What do I mean by error paths? Error paths are those paths where the test function could have returned an error code. How do we know that? We have an error specification that says for each test function what kind of values it can return for an error. Okay, now we have our error path. How do we figure out if something is a bug? We look at if the error is handled properly. And to do that, we consider 3 general error handling methods. The first method is just logging. The second method is passing the error upstream through, say, return value or another method. Or, more drastically, the program terminates with an error code. If none of these happen, we say that the error is unhandled and we have a bug. Okay, I glossed over some details about passing the error upstream because the error does not always have to be completely, exactly passed upstream. Sometimes it's perfectly okay if there are some transformations done by the caller in returning an error code. How do we handle that? That is why in our error specifications we also include an error protocol. And that is something that the program follows. What I mean by that is that the caller functions in the program follow this particular protocol by returning error values that have to fall inside a particular range. So as long as a caller returns a value inside that particular range, then we consider the error as being propagated and handled. Now, the way we focus on the caller makes it very easy to localize the bug because we consider the bug to happen at wherever the caller first stopped handling the error. Because if it doesn't handle the error and doesn't even propagate the error upwards, then there's no real reliable information afterwards that let us know how to handle the error. But no tool is perfect, and EPEx will make mistakes if the error spec or path exploration is wrong. If the error spec is wrong, then some paths will be wrongly classified as error paths. If path exploration is incorrect, then some infeasible buggy paths will appear. These imperfections will generate false positives, so we need to cut them down somehow. To do that, we compare across the call sites of the same test function. That lets us find inconsistencies in error handling, and that's how we prioritize them for reporting. For example, if the failure of a function is ignored in all the call sites, we do not report them. So this is how all the paths Oh, yeah, let's see. Oh, might just be that slide. Weird. Okay, well, that's embarrassing. Well, where was I? Anyways, what you just saw, well, what's the summary of, happened to be the summary of all the parts I just mentioned, so, well, you already know about them. But point is that user inputs the code and the error specifications, which lists what all the error values are for the functions, and as well as the error protocol for the whole program. And eventually that passes through all the different steps until the user gets a final bug report. Now let's see how EPEx works by using an example. Let's look at the GnuTLS bug that we talked about earlier. We start doing under-constrained symbolic execution inside the caller, and because it calls checkif CA, we symbolically execute that one also. So let's look inside. Let's see what happens if result is non-negative. When that happens, result is set to 0 and returned. Now we look at our error specification, we see that checkif CA returns a negative value for an error. That means the 0 is not an error code, and this path is not actually an error path, and we stop exploring it here. Now let's see what happens inside checkif CA if the result value is less than 0. Then the function skips to the end, returns the same negative value, and we know because it's a negative value that we have an error path, and we have to make sure that the error is handled within the caller. But we see that result is set to 1 and returned. And if we look at our error specification, the error protocol for GnuTLS says that 1 is actually the one value that is not an error value. Now, we have not come across any exit functions. We have not come across any warning or error logging functions. That means that this error is unhandled, and we actually do have a bug. Now, I've been talking about error specification so much, you're probably starting to wonder, how hard is it to create that? And my answer is not that hard, because most functions only follow a few, or most functions only follow a few error codes. Usually they just return some kind of macros or enums, and that's how we can easily figure out what kind of error codes a function can return. In fact, we created error specifications for 256 functions, but there are only 38 unique specifications. And the table shows for some of the programs some of the common error conventions that we saw. Reusability gets even better while testing library functions that are used across many applications, because then we can use the same error specifications for all those applications. And finally, we do have an automated way of generating error specifications automatically. We created a tool called EPEx, and we'll actually be talking about that at another conference called ASE, actually. It's next month. It's on automated software engineering. Now, that's it for the principles behind EPEx. To put it to use, we implemented a Clang checker. Clang contains a static analyzer engine that lets us do under-constrained symbolic execution on C code. And it also lets you plug in your own checker, which is a class where you override certain callback functions to interpose the path exploration and check the symbolic state during symbolic execution. These are some of the callbacks we used. The checker itself is 617 lines of C++ code, and the last filtering step is a Python script with 227 lines. We ran EPEx on 867,000 lines of C code. We used EPEx on 9 popular open source software projects. 4 of them are SSL or TLS libraries. The other 5 are applications that use OpenSSL. Here's a brief summary of the results. EPEx reported 132 bugs. Out of those, 102 of them were real, and 28 of them were false positives. That's a precision of 78%. That's it for how precise EPEx is. Now, how fast is it? Here are their run times. The leftmost column says which programs we looked at. The second column gives the time. Second column gives the time for compiling the project without any checkers. The third column says how long it took to use the division by 0 checker, which is another checker that comes with Clang. The last column is our time for EPEx. As you can see, EPEx is actually slightly faster than the standard. EPEx is slightly faster than the sample checker that comes with Clang. That's because we only look at the error paths. And yes, it is also much slower than not having a checker at all, but it's but it's still fast enough to be integrated into processes like nightly builds. Now on to some real bugs. Note that all these bugs have been reported and confirmed by the developers. In the first example, we see that the error is not checked in the highlighted code. In fact, the return value is not even read. When the output is used later, corrupted data will be read instead. Well, it's pretty easy to check if no check is happening, but let's see what happens when there is a check, but the correct value is not checked. So here, rand pseudobytes is called, and it returns 0 or -1 for an error. When that happens, you really don't want to use its output, because that means your secret or random value will not be random. Here, the initialization vector is supposed to be randomized, and the caller only checks for the negative value, not the 0 value. That means that the initialization vector might not be random, which will make the encryption much easier to break. The last two bugs are especially tricky because the checking is correct, but the handling is not. In this function, we have the caller trying to generate a key. It does an exponentiation function that can fail, and if it does fail, it returns the variable s. Now, according to our error protocol, a function that returns a pointer should return a null value. But if we have reached this exponentiation stage, that means that we have actually allocated s properly. And when returning it, we are returning something that is not null and looks proper, even though because we skipped to the end. So it looks like that s is valid, but the value is not even initialized. That means our key is going to be either weak or broken. This last bug happens in GnuTLS as part of the online certificate status protocol. This is responsible for revoking certificates. In case of an error, what should happen is the time value, which is a parameter pointer, and the return value should both indicate some kind of error. But as you can see here, only the time value is set to a negative value, but the value that's being returned indicates success. It gets problematic when we see where it's being used. In the caller, only the return value is checked, and the time is used. And at the bottom, we see the comparison, and that's not correct because it is using an invalid time value. Now, this is it for the bugs that we've seen that EPEx reported. Now, let's look at Now that we have looked at the bugs that EPEx found, let's look at the false positive that EPEx reported. We noticed that many of the false positives are because of limitations of Clang's symbolic execution engine. Clang only looks at one source file at a time. So if we have multiple files, and we have one file calling a function that is defined in another file, then Clang will not do symbolic execution in that called function. And that's going to lose a lot of information that we could have otherwise used. Here on the right side, we see the caller calling the function x509getZeroNumber. And that function can return a null value for an error. And that potentially null value is called to the integer duplication function. And that might look pretty bad because you might be dereferencing a null value. But if you are looking at the source code, we see that actually the string value, the potentially null value, is being checked. And when that's being checked and it's null, then the function returns null back to the caller, which, as we can see, it actually checks for the value. So we actually know that if we had seen that the second function actually returns null for an error input, then we would have known that it's checked. Luckily, this is not a fundamental problem of EPEx. EPEx is not tied to Clang. It is applicable to any symbolic execution engine. So as symbolic execution engines improve, we will have less of these false positives. To sum it all up, improper error handling is a silent but deadly problem. As you saw, it's behind a lot of serious security vulnerabilities. But it is also tricky to find with existing tools in a scalable and reliable fashion. EPEx scalably handles the problems of detecting and localizing these bugs. I encourage you to start using it now. Our code is available on GitHub. Thank you. And at this time, I would like to take any questions.
How much does your work rely on good test coverage for these libraries?
You're saying that, what do you mean by test coverage of libraries?
Oh, you were saying you use symbolic execution to trace the error propagation?
Oh, yeah.
So does this rely on these libraries already having a test harness that you piggyback on, or how?
Oh, no, we don't use those. What we use is, okay, so we're talking about Clang, right? And it actually comes with a script that lets us hook into the build environment for, say, the make file, and replace certain environment variables and such that lets us pretty much run Clang alongside the compiler. So the checking is done during compilation, so we don't actually look at testing. And usually, maybe looking at testing might be a bad idea because there they might not care as much about error handling as in real usage.
Justin Kapos, NYU. So did you disclose these bugs to the vendors, and what was their response? Did they confirm all the bugs that you had listed there?
Yes.
Or?
Okay, let's thank the speaker again.